Hello everyone, I'm Peng from Fudan University, China. Welcome to my talk, Multidimensional Analysis of Cloud-Native Software Based on Large-Scale Operation Data. In this talk, I will first introduce the concepts of cloud-native software and the microservice architecture. Then I will explain why cloud-native software evolves to complex ecosystem. After that, I will analyze the challenges and opportunities of cloud-native software analysis. And finally, I will share some past and ongoing work for multi-dimensional analysis of cloud-native software. Cloud-native software has been a very hot topic in both industry and academia. Cloud-native means that the design and the implementation and the deployment of an application fully exhibit the characteristics of cloud computing, for example, distributed and elastic. Cloud native means a lot of things. Among them, I think the most features include microservice architecture, container-based deployment and operation, and DevOps and continuous delivery. According to IDC, by 2022, 90% of all new applications will feature microservice architectures, and 35% of all production applications will be cloud native. Microservice architecture is very important for cloud native software. Microservice architecture means to implement an application as a set of small-grained services. Each service can be developed by a small autonomous team and can be independently released, deployed, and scaled. Cloud-native software can be very large. We can see in some very large companies, their cloud-native software can include tens of thousands of services. This kind of cloud-native software includes many applications. These applications share common service infrastructures and the boundary of the applications fades. And in this kind of software system, new features and business continually emerge every day. And the services of the system continuously delivered and added and updated. So we think this kind of complex system can be regarded as a new kind of software ecosystem. And this kind of software ecosystem, I think, is quite different from traditional software ecosystem like Android and Apple ecosystem. Because for this kind of cloud-native software ecosystem, the whole applications and the services are continuous in operation and their evolution are mostly online. We all know that software analysis plays an important role in software engineering. They can be used for different purposes, for example, reverse engineering, fault detection and testing, design issue detection, and debugging. And traditionally, the techniques used for software analysis include static analysis, dynamic analysis, and history analysis. Among them, static analysis, which means to use some kind of static analysis tool to analyze the source code, and history analysis, which means to analyze the evolution history of a software, usually by analyzing the commit history of a repository. These two kinds of techniques are mostly used. Dynamic analysis is less frequently used in traditional software analysis because dynamic analysis is usually very expensive. But for cloud-native software, we will be faced some new challenges because the services in cloud-native software are developed independently by different teams and in different repositories and running in a highly dynamic and uncertain environment. And for this kind of cloud-native software, the complexity of the system has been shifted from individual services to architecture level because we know that the services of the system can be very small. So the development of the individual services is not so difficult, but the complexity is quite large at the architecture level because, as I mentioned just now, for a large software, cloud-native software, it can include tens of thousands of services. And this kind of architecture cannot be managed in a top-down way because the system is too large and different parts of the system are developed by different teams. So nobody can have a very complete big picture of the whole architecture. And for this kind of software, static analysis or history analysis cannot help, because we know that each service in cloud-native software has its own repository. So it means that if we analyze the source code or the evolution history of a repository, we can only understand the individual services. We cannot understand the interaction between different services. But at the same time, the analysis of cloud-native software has some opportunities. First, cloud-native software follows microservice architecture, so it means that this kind of software has an explicit software architecture, because the architecture of cloud-native software is naturally defined by the services and their interactions. So we say that this kind of cloud-native software has an explicit software architecture. At the same time, cloud-native software usually has very good infrastructure, including the so-called observability infrastructure. Observability for cloud-native software and the microservice architecture includes 3 pillars. They are tracing, logging, and the metrics. So it means that based on this kind of infrastructure, we can obtain very rich and large amount of data from their runtime infrastructure, including logs, traces, and the metrics. And this kind of runtime data, that is so-called operation data in this talk, can help us to do different kind of analysis. So based on this kind of operation data, we can do a lot of analysis. So here I will talk about multidimensional analysis from 4 different aspects. The first is anomaly detection. The second is root cause analysis. The third is architecture evaluation. And the fourth is business understanding. Anomaly detection and the root cause analysis both are concerned with short-term problem handling. For example, detect the anomalies and identify the root cause in a very short time to help the developer to resolve the problem or incidents in a very short time. Architecture evaluation and business understanding are more about some medium or long-term goals. For example, architecture evaluation will be concerned about the long-time evolution of the software architecture. Anomaly detection means to detect possible anomalies or incidents in the running system. In traditional distributed system, log analysis has been widely used for anomaly detection. Usually, they will extract log events from raw log messages and treat a log as a sequence of log events. Then they can learn log patterns from normal execution and detect anomalies when log patterns deviate from the trained model. In recent years, there are some researches focused on trace anomaly detection. They treat a trace as a sequence of service invocations and learn similar to log anomaly detection. They will learn trace patterns from normal execution and detect anomalies when trace patterns deviate from the trained model. But at the same time, we think that the current log anomaly detection and the trace anomaly detection approach have some limitations. Because we know that a microservice system can include many different many services running in different nodes. So to understand the whole behavior of the whole system and to detect the anomalies and we need to combine the behaviors of all the services and also their interaction. So we think that we need to combine logs and the traces together, because the logs reflect the intra-service behavior and the traces reflect the inter-service interactions. We need to combine them together, and also we need to consider the complex structures of traces, because we know that a trace indicates an invocation chain for a request. In a trace, there may be many service invocations in the hierarchical structure, and at the same time, a trace may include a parallel or a synchronized invocation. So we need to consider the complex structures. Root cause analysis means to localize the root cause of a given incident or anomaly. Usually, we can combine different kind of operation data, including logs, traces, and KPIs for this purpose. In the recent work, we use service dependence graph to do root cause analysis for specific types of anomalies, including performance, reliability, and traffic. In this work, we construct a service dependence graph. In this graph, we have service dependencies and the related KPIs, which are captured from recent service invocations. The basic idea of this work is to traverse the service dependence graph from the entry node for root cause localization. The entry node means that where the anomaly or incident is reported. The key techniques in this work include single service anomaly detection, which means to determine whether an individual services is anomalous based on the KPIs. And traversing strategy means how to traverse the service dependent graph in the efficient way. Pruning strategy, which means to prune during doing some kinds of pruning during the traversing, because we know that the graph can be very large. So if we have no pruning strategy, the whole process will be very inexpensive. Candidate root cause ranking, which means that to rank all the candidate root causes in the last step. So the challenge in this work is how to balance between the accuracy and the time of root cause analysis, because we know that if we want to obtain a very precise result of root cause analysis, we can use more time, for example, to traverse the service dependent graph in a better way. But at the same time, we need to control to limit the time of the analysis, because we know that we are handling runtime anomalies and incidents. So the developers need to resolve the problem in a very short time. Microservice architecture is likely to decay. And I think the causes for this problem maybe come from two aspects. First, microservice architecture usually is ongoing a very long evolution, and during the process, as the different parts of the architecture are maintained and developed by different teams, different kinds of issues will be introduced to the architecture. At the same time, as I mentioned just now, the Microsoft architecture of cloud native software can be very large. So it means that usually there are no global view about the whole architecture. So different kinds of architecture issues may emerge. For example, we can see in some very large industrial microservice systems, there exists a very long invocation chain. For example, I have seen some invocation chain include about 500 hops in a single trace. And also there are some cyclic invocations in some traces. And also, as you can see in these slides, there are also other kinds of architecture issues. For example, hub-like dependence, and also no cohesion and high coupling of services. And also, there are some architecture issues related to performance, availability, and scalability. Architecture evaluation for cloud-native software based on microservice architecture highly depends on operation data, not source code and evolution history. We know that architecture evaluation usually conducted for traditional software based on source code analysis and evolution analysis. For example, we can analyze the evolution coupling relationships between different kind of files based on the repository. But as I mentioned just now, because for microservice architecture, each service can have its own repository, so it means that we cannot analyze the relationship between different services from the repository, because each repository only records the history of a single service. Also, at the same time, source code analysis cannot help a lot for similar reasons. So I think for microservice architecture, the evaluation, I think, highly depends on operation data. That means that we should consider to use traces, logs, and also KPIs to identify the potential architecture issues for cloud native software. Basic understanding in a similar, I think, for similar reasons, usually the developers cannot have a complete picture or view about the whole microservice system. So similarly, I think we can use the operation data to understand the business. In a recent work, we have present approach that conduct a multi-layer aggregation of traces to help the understanding of business. In this work, we conduct multi-layer aggregation. That means that in one layer, we aggregate the traces by the topology. That means that all the traces having the same tree structure will be aggregated together. And in another layer, we will further aggregate the traces based on business scenarios. The business scenarios here can be indicated by key services. For example, for given a trace, if the trace has passed some key services, for example, order submission and also payment, then we can say this trace is about online shopping. Yeah. So based on this kind of multi-layer aggregation, we can have a more efficient view about the trace, because we know that the raw traces can be very large. For some big microservice systems, they can produce billions of traces per day. So we need to use this kind of aggregation approaches to provide a more efficient view for the understanding of the whole system. So in this work, we combine graph databases and analytics databases for efficient trace data analysis. And also we provide some visualization for the developers to understand the business flows and their changes. So we can see, based on this kind of analysis, we can provide a visualization of the current business flow, and also we can highlight the changes. For example, maybe this morning the development team have do some. They deliver some new features, and then the business flow have some changes. So based on this kind of visualization, we can understand what changes has happened for the system. So conclusion, multi-dimensional analysis of cloud-native software is very important. So, but we need to know that large-scale cloud-native software has evolved to complex microservice ecosystem. And for this kind of complex ecosystem, multi-dimensional analysis is required for various purposes, such as anomaly detection, root cause analysis, architecture evaluation, and business understanding. But at the same time, different from traditional software analysis based on source code and evolution analysis, cloud-native software analysis highly depends on operation data, including trace, log, and matrix. Our vision for multi-dimensional analysis of cloud-native software, including that operation data analysis can be used as a means for observing and governing the cloud-native software ecosystem. And at the same time, the so-called AIOps may need to extend its focus to include such as architecture decades and business view recovery. And we need to consider to introduce more and richer operation data by new sensors to improve the observability. And also we need to consider to use more intelligent operation data analysis techniques by combining trace, log, and matrix. Thanks.